Thank you, Professor Bautic, for the introduction, and thank you all for being here with me today. Within the thesis, just a second. Within the defense presentation, I'll try to give you a short overview of all the steps needed to deploy the model predictive control, MPC, for zone temperature control on a full-scale skyscraper building. So at the beginning, why buildings? It is well-known fact that buildings consume around 30% of total energy consumption worldwide. If we dissect this 30%, we can see that the largest consumers of the energy within buildings are systems for maintaining thermal comfort. Energy efficiency improvement of these systems is thus identified as very important for reducing the overall energy consumption in buildings. Over the past few years, many terms have been used in the building sector to describe the latest technological advances, particularly for energy efficiency. Smart buildings, big data, Internet of Things are just a few of the most commonly used ones. The subject focus of all the terms was digital information from the building and energy. The key focus of my research was put on the MPC algorithms utilized for building climate control. MPC is an advanced control strategy which exploits the possibility of prediction of near future building behavior. So how this works for a building? There is a building to control and mathematical model of that building which is used to predict its future behavior. Based on the model, desired system behavior, system constraints, and predictions of weather and possibly other relevant predictions like energy price or occupancy, at each time step, the optimal control problem is formulated and solved. The result of the optimization problem is a sequence of future control inputs which ensure the optimal system behavior with respect to the optimization problem. At each time step, only the first control input is implemented on the system. The optimization problem is then recreated and resolved at the next time step by using new measured values from the system and new predictions. By this so-called receding horizon strategy, feedback is introduced into the system. The MPC approach applied in building energy management systems has been recognized as one of the most promising solutions for improving comfort and achieving considerable energy savings. However, despite its advantages, its practical implementation is still a major challenge, which is evidenced by a small number of experimental verifications performed until today, and to my best knowledge, 0 commercial deployments. This is why today I'm very proud to say that we implemented MPC to control temperature in the skyscraper building of the University of Zagreb, Faculty of Electrical Engineering and Computing. To enable the deployment of the MPC algorithms, the case study building is equipped with additional hardware and ICT solutions on top of already existing building automation system. Meteorological station on the building rooftop, including solar irradiance measurement, software-wise updated digital zone temperature controllers, additional one-wire return medium temperature sensors installed on all controllable fan coil units, colorimeters installed on major supply lines, communication controllers, server, and database, all funded from European, national, and internal faculty funds. Weather forecast service is provided by the Croatian Meteorological and Hydrological Service. It is inherited from our joint project Enhanced Buildings, which ended in 2015, and it's still maintained for free, for which we are very grateful. To keep the operation safe, 3 basic features are ensured in the building ICT infrastructure. The first one is software switch, which enables to easily switch, to easily activate or deactivate MPC control in individual building zones. The second one is so-called heartbeat signal, which is used to monitor the performance of the software code implementing the MPC and switch operation back to the classic operation if some error is noticed. All measured building variables are collected into the two-way real-time database, which also contains the commands for fan coil unit fan speeds when MPC is applied to the building. The interaction of the building end users with the climate control system is completely the same as before, which means that MPC is completely invisible to them. The zone operation via MPC is enabled to the SCADA system, which means it is enabled by the authorized person. And even then, the zone temperature is controlled by the MPC only when the user selects auto mode on its wall unit, which reflects the user's desire to maintain the selected zone temperature. Besides the SCADA computer, there is also an optimization server that implements the real-time database and runs the software modules implementing the MPC for zone temperature control written in Python. The underlying mathematical programs for MPC are solved by using the Cplex optimization solver. So how did we start? We started pretty much like this, by having an idea and being quite confident that we will be able to do it without any problems. However, we all know that in reality, nothing is as expected. So in reality, we had to overcome many problems and obstacles before we were able to run the MPC. The first obstacle is mathematical model of the building. The practical experience has shown that acquiring the MPC essence, the model, is the most time-consuming and costly part of the MPC implementation. The mathematical model of the system can be obtained in three basic ways: by using physical, semi-physical, or non-physical modeling, which are also often referred to as white box, gray box, or black box modeling. Physical modeling relies on fundamental physical laws and detailed physical specification of the process to be modeled. Opposite to physical modeling, non-physical modeling is completely based on the data, so nearly zero knowledge about the system is used. Typical examples of this approach are, for example, neural network. And in the middle, we have semi-physical models, which use the best from the physical and non-physical approach in a way that the model structure is assumed based on the physical knowledge, and model parameters are estimated based on the data collected from the building. This way, the compromise between the model complexity and accuracy is achieved. White box models are very expensive to build and unsuitable for MPC due to the nonlinearity and high order. On the other hand, black box models are very low cost, but usually are not in a form suitable for MPC synthesis. Gray box approach combines the best from both approaches, resulting in a model which is suitable for MPC synthesis, but it's still not easy to get it. The goal of the identification methods developed within the thesis is to make the gray box models easier and less expensive to identify, enabling thus fast deployment and replication. To be able to find relation between thermal energy to the building zone and zone temperature, first we have to find a model of the elements used for provision of the heating, cooling energy in building zones, FENCO units, which are often found in commercial buildings. To do so, we assumed a physically based model structure and identified the unknown model parameters based on the data available from the manufacturer's catalog and real measurements collected from the building. Thermal power provided by a FENCO unit depends on the following 5 variables: supply medium temperature, which is assumed to be equal to the temperature measured by the first upstream calorimeter since the pipes are isolated, medium mass flow, return medium temperature, fan state, and zone air temperature. All required variables except the medium mass flow are measured directly with digital sensors. Measurement of flow on every unit would be too expensive, so we opt to identify flow shares between a group of FENCO units whose overall medium mass flow is measured by a common calorimeter. The number of FENCO units in a group is typically between 11 and 17. The solution to do it is to represent the heating cooling installations with an equivalent electric network. Every hydraulic resistance element in installations, meaning pipes and FENCO units, is represented with its equivalent electric resistance. The only difference is that instead of using linear Ohm's law, now we have non-linear function between the equivalent voltages, currents, and resistances. The individual flows are then found through solving a simple non-linear optimization problem. Since in the case study building, there are no valves on FENCO units, meaning hydraulic situation in the building is static, once identified flow distribution is valid for a wide range of central heating pump operating points. The approach was applied to all floors of the case study building to identify the medium mass flow distribution through all controllable units. The graph here presents the distribution of the medium mass flow among FENCO units on the 9th floor, south side supply duct. The main supply line branches left and right from the calorimeter. It can be seen that the medium mass flow distribution is far from uniform, and expectedly, the units which are further away from the supply receive the least flow. So once we are able to determine the medium mass flow to the unit, we have all data required to identify the thermodynamic FENCO unit model. Thermal power provided by the FENCO unit to the zone is modeled by a first-order switch linear model, where fan speed is used for switching. It basically means that for every fan speed, there is different dynamics, which is caused by different overall heat transfer coefficient function U, which is modeled as shown on the slide. The unknown heat transfer function depends on the medium mass flow, so to cover different operating points of the system, non-uniform distribution of the medium through the system was exploited. More detailed identification procedure is presented in the thesis, and here we focus only on results. The identified model is experimentally validated by performing multiple tests on several different FENCO units. This slide here shows the results of the simulated return medium temperature and measured one. And also it shows the thermal power, which is compared with the thermal power measured by colorimeter. We can see that we have good alignment between simulated values and measurements. Besides the hydraulic and thermodynamic model, there is also a model of electrical energy consumption of fan coil unit. Although the electrical consumption of a single fan coil unit is low, the overall consumption of all fan coil units in the building is on a level of almost 30 kilowatts. All three models together form an energy model of a system of fan coil units. Once it is identified, we are able to develop a software module which runs with a minute time step and calculates the electrical and thermal power of every unit in the building. The software module reads the current values of the zone temperature, fan speed, return medium temperature, as well as the medium mass flow and supply medium temperature from the colorimeter. And based on those data and identified model, it calculates current thermal power provided by the fan coil unit to the zone air and electrical power generated by the fan coil unit's fan. Since we have available colorimeter measurements which measure the overall energy consumption of a group of fan coil units, to verify the model performance once again, we compare the thermal energy consumption of one group calculated by the colorimeter with the one calculated by the software module. The good agreement between these two shows us the way how to reduce the unnecessary sensors and increase the cost effectiveness of the MPC algorithms by replacing some of the sensors with software solutions. The building thermodynamic model, which gives the dynamic relation between thermal energies provided to the zone and zone temperatures, can be well described with two states. The first state is air temperature inside the zone, and the second state is equivalent to all elements with higher thermal capacity than air, like walls and furniture. The inputs into the model are outside air temperature, solar irradiance incident on the exterior building surfaces, and thermal power provided by a heating cooling element. To avoid multiplications and divisions between unknown thermal resistances and capacitances, the model is rewritten into the state space form. Since the system state Tz is generally not measurable, to identify the model, we have to estimate both states and parameters, which end in a nonlinear identification problem. So this is why we opt for unscented Kalman filter-based identification framework, in which parameters are treated as dynamic variables itself. To enable the use of the model with an arbitrary sampling time, the identification is performed for a continuous time model. The basic UKF form is extended by including known parameter limits, finding a convenient way of selecting the filter sampling time, and dealing with inconsistent system excitation. The UKF is based on unscented transformation. In unscented transformation, minimal set of sample points is selected, so-called sigma points, and it's propagated through a nonlinear function. And it's then used to reconstruct the Gaussian distribution of the propagated and weighted sigma points. In constrained unscented Kalman filter, the parameters can be limited to their physically meaningful values. For example, we are 100% sure that all parameters in our semi-physical building model are non-negative. One simple solution to do so is so-called clipping, where all sigma points outside the constraints are set to the boundary. The approach which we decided to rely on is to reduce the original unscented transformation spread delta in amount required to keep the sigma points within the boundaries. To counteract the asymmetry of the obtained sigma points after including the constraints, in a thesis, it is
we have lost your sound, Anita.
I think microphone is muted.
Microphone is turned off.
Muted, yeah.
Okay, what was the last thing you heard from me?
Like 15 seconds ago, so this slide just.
Okay, is it on this slide here
this
or
slide.
The previous one?
This one, yeah.
Okay, so after we included the constraints, the sigma points are no longer symmetric. So to counteract the asymmetry in the thesis, it is proposed that the weights are properly changed in a way which assures positive definiteness of the covariance matrix. While many approaches in the literature suggested using linear reformulation of original weights, which results in both positive and negative weights, we decided to propose FN reformulation, in which only the weight related to the mean V0, which is selected to be equal as in the original algorithm, may be negative. Since The weights are used to reconstruct the Gaussian distribution of the propagated sigma points. Strictly positive weights ensure numerical stability of the algorithm and keeping the covariance matrix positive definite. The methodology is applied to all 248 building zones. The algorithm was able to identify the parameters with less than 1 week of operation data, which of course have to be recorded during periods where building was unoccupied, like for example, winter holidays here. After the identification was done, the suitability of the models to be used for prediction within MPC strategy is tested. First, the identified model is used to estimate slope dynamic temperature during the considered time period used for verification by using simple linear Kalman filter. After that, the model performance is simulated in an open loop fashion for prediction of temperature behavior 24 hours in advance without any feedback used during that period, and compared with the real temperature measurements during that interval. The graph on this slide here presents the comparison between the temperature predictions of both slow and fast dynamics calculated by the model and the real temperature measurements. The suitability of the model to be used for prediction of the building behavior is tested for 4 different prediction horizon lengths from 6 to 24 hours in the future. Despite the uncertainty of the input data, average mean square error for minutely sampled 24-hour-long prediction of all building zones is on a level of 0.3 degrees Celsius, which proves the suitability of the identified model for control and fault detection purposes. And also important when compared with the standard UKF and constrained UKF form, which can be found in the literature, the difference in the number of steps with numerical problems due to the ill-conditioned covariance matrix is evident. If we return a little bit to our identified building model, we can see that besides the variables which are included here as inputs into the model, we know at least several more variables which affect the dynamic of the building temperature. Window opening, shading position, electronic equipment, people. Since the impact of those variables to the zone temperature cannot be measured, we treat them as disturbance. To account for the impact of the disturbance to the zone temperature, the identified model is augmented with an additive disturbance input PD. Due to the similar nature of thermal inputs PA and PD, their impact on the zone temperature is modeled with the same parameters, so no need for additional identification. To estimate the unknowns, now only slope dynamic system state TZ and heat disturbance PD, simple linear Kalman filter is used. Linear Kalman filter operating on 1 minute timescale is implemented in Python and deployed on the server. The algorithm uses current measurements of zone temperature, thermal power provided by the FENCO unit to the zone air, and measurements of the outside weather conditions from the building meteorological station to estimate the unknown variables. The first graph presents the measured air temperature and estimated slope dynamic temperature. The difference in the dynamics of those two states is evident. The second graph presents the estimated heat disturbance expressed in kilowatts. By in detail examining the obtained results, it can be concluded what was happening in the building zones. So, for example, if the windows were opened or if the building zones were even occupied on a certain day. The historical values of the estimated heat disturbance are used to predict the user behavior and utilize that prediction to achieve energy savings and increase the user comfort. Finally, after we explained tools for needed identifications and estimations, we can focus on MPC. The approach which we decided to use differs significantly from other reported building MPC approaches in the decision to have heating or cooling energy as decision variable. By doing so, the interaction of the zone climate control with other building subsystems through an energy link is enabled, as well as high level of modularity for different heating cooling elements in building zones. The drawback of such approach is that the unmodeled disturbances are no longer directly compensated. So besides the standard modules, which are used for prediction of heat disturbance, user behavior, and weather, we need to include the previously discussed estimator into the control loop. Also, additional interface module is required to ensure realization of optimal thermal energy inputs by properly selecting control actions on heating cooling elements, such as fan speed in our case. The sampling time of the centralized MPC is selected to be 15 minutes, while heating cooling element interface and online estimator operate with 1 minute time resolution. The main focus of our MPC is put on the end user's comfort, which is expressed by following constraints. So every user in the building can select the desired temperature, and the building maintenance crew can choose flexibility to temperature changes delta. The parameter delta is usually selected as a number between 0.5 and 1.5 degrees Celsius, which is in accordance with thermal comfort standards. The MPC approach, which ensures minimization of energy and following of the user-defined temperatures, is well known as setpoint tracking. This approach, combined with the receding horizon strategy, often results in either minimum energy performance or in permanent setpoint tracking. A compromise is made through the weighting factors Q and R, which should be selected properly to enable easy weighing. Since U is related to energy and it's normally expressed in kilowatt hours within one sampling interval, and the setpoint deviation is in degrees Celsius, to make them comparable, both parts of the optimization criterion have to be brought to the same units. To do so, the known sensitivity of the zone temperature to thermal power changes is calculated based on the identified building model. This way, both parts of the optimization criterion are expressed in the same units. So now we can easily switch between the desired system operation by changing the trade-off parameter gamma. For gamma equal to 1, both energy consumption and reference tracking have the same weights, so controller will decide what is the best compromise. With gamma lower than 1, the controller will maintain the temperature at the temperature boundary most of the time, and large energy savings will directly be a result of the deviation from the reference. For gamma larger than 1, the control focus is put on following the energy reference, even if such behavior will lead to increased energy consumption. So once we know how to calculate optimal thermal energies per building zones, those thermal energy needs to be deployed on Fenco units. The realization of thermal energy requests calculated by the previously described MPC for current 15-minute long time interval is ensured with the local controllers for Fenco unit control. If the power would not be quantized by discrete fan speed, we could operate minute by minute within constant power like this. However, since there are only 3 possible fan speeds plus off states, the energy profile obtained with the Fenco unit will probably look like this, meaning more or less energy than requested will be generated. To compensate this mismatch at every minute time step, the difference between the energy provided into the zones within current 15-minute interval and energy requested is calculated. Based on that difference, algorithm has to correct the interface energy reference on the rest of the prediction horizon. By doing so, the energy at the end of the central MPC interval is as close as possible to the requested one. Besides realization of the requested thermal energy, the local MPC for Fenco units has a task to compensate for unaccounted disturbance changes, keep the temperature within the limits, prefer the lower fan speeds, minimizing thus the electrical energy consumption of a fan and reducing the noise, and reducing the number of the switchings between different fan speeds. The unaccounted disturbance changes imply the difference between the current estimated heat disturbance values and heat disturbance predicted and used in the central MPC for the current time interval. By compensating this mismatch, offset-free control is assured. The final optimization problem is in a form of mixed integer linear programming due to the discrete states in the identified Fenco unit model. Within the next few slides, I'll give you some results of the real-time implementation of MPC. So here is the example of the weather forecast and real weather measurements used for calculation of the optimal thermal energy profile for the building calculated at 22 hours on 24th of February. Dashed lines denote forecast available exactly at 22, while solid lines represent the realizations. Since we have local measurements, for the first time step, local measurements are used. This is the reason for large difference in temperature between the first and second step in outset temperature. The comfort in one selected zone is defined with the temperature set point of 22.5 degrees Celsius between 5:30 in the morning and 21. The user comfort requirements are assumed to be equal as in the same week 1 week ago to capture the user behavior repeatability. In all building zones, comfort savings trade-off parameter is set to 1, and flexibilities are set to 0.5 degrees Celsius. Although the heat disturbance was assumed to be constant on the prediction horizon, the predicted temperature profile and the predicted thermal energy are similar to the realized one. The difference is only due to the prediction errors and other errors in prediction of other relevant input data, which are handled through the receding horizon principle. The most important, the user comfort is kept within the defined limits, proving us that the interface module is working as expected. Here's another example of the interface module operation in one north-oriented building zone. On 11th February, the user requested set point is 23 degrees Celsius between 5:30 in the morning and 20, and the user flexibility is 0.5 degrees Celsius. The interface selects the fan speeds, which assure the thermal comfort within the defined limits, minimal number of fan speed changes, realization of the requested thermal energy, and preferably operation in lower fan speeds if this is possible. The graph here illustrates the difference between the energy requested by the centralized MPC and the energy realized by the fan coil unit. The difference is due to the predicted heat disturbance errors, as well as inability to perfectly follow the energy reference because of the limited number of the possible fan states. One of the reasons why we decided to take the harder way by controlling the thermal energy in state of temperature was the ability of synchronization with other building subsystems through an energy link. Almost all building subsystems are interconnected in some way. However, they are usually controlled independently and without coordination with local energy storage possibility or local energy production. So there is only a weak or even non-existent coordination between them. Many such operated buildings connected to the same grid can cause large peaks or sags of energy consumption on the grid, which can be costly both to the building operator and both in grid operator. All this leads to one natural question. What if we can orchestrate the building subsystem mutually and with the grid, and how can we do it? And this is where the TreeSmart project comes in. The objective in the TreeSmart project was to separate building subsystems in a hierarchical fashion and coordinate their operation through modular parametric hierarchical coordination, rather than having one large optimization problem that handles all building subsystems at once. The considered building energy management system in the case study building consists of 3 levels following zone, central HVAC system level, and microgrid level. HVAC stands for heating, ventilation, and air conditioning. The zone level, as the lowest level in hierarchy, is in charge of shaping the thermal energy consumption in building zones. By additionally including the central HVAC system, the benefits are increased since conventional control approaches are unable to take into account current and near future energy requirements from building zones. The microgrid introduces the possibility to manage controllable sources, storages, and loads to optimally shape energy exchange with the distribution grid. If no other level than building zones is available, then the energy price can be transferred directly from the grid to the zones, but it first has to be transferred from euros per kilowatt electric to euros per kilowatt thermal by using central HVAC system coefficient of performance. The interaction between the levels is done by so-called price consumption talk. The lower hierarchical level states its consumption to the higher hierarchical level. Higher hierarchical level then optimizes its behavior with respect to the energy stated by the local hierarchical level and practically says, okay, I know how much energy you want to spend, but this will cost you this much euro. However, I'm also giving you a price sensitivity so you can reschedule your operation to perform better euro-wise. The research done on this part would never be possible without my colleagues from Laboratory for Renewable Energy Systems, who were intensively working on the modules enabling MPC control on higher building hierarchical levels. To include building zones into the coordination with other building subsystems, first, the optimization problem is redefined by including the price of the energy and price of the comfort. Comfort price can be, for example, selected as the mean price of the thermal energy along the prediction horizon. The coordination between the zone and central HVAC system level is done by sending the optimized zone energies and temperatures to the central HVAC system. Central HVAC system that optimizes its behavior with respect to the defined thermal load from building zones and communicates the localized cost of its electrical energy consumption to the zone level, together with the critical region, which is consisted of constraints on zone thermal energies and temperatures for which the stated prices are valid. The zone level also receives the future plan of the central HVAC system operation, meaning supply medium temperature and flow, which enable better planning of the fan unit operation in building zones and higher energy savings. The coordinated building behavior is validated for a typical summer day for day-to-day building operation. 4 different control algorithms were tested. Baseline operation, which represents current building control, which means that we have hysteresis controller, which controls the building zone temperatures. We have scheduled operation of the central HVAC system and typical operation of building microgrid. The energy optimal operation denotes the operation in which only energy consumption is transferred from lower hierarchical level to higher hierarchical level without any feedback on the price. Only microgrid knows the actual price in money. The price optimal operation denotes results obtained by utilizing the model-like hierarchical coordination. The electrical energy prices, as well as the peak power prices, are selected to represent the realistic conditions. The volatile electrical energy prices are lowest in the morning and reach the highest values around 8 in the morning and 8 in the evening. The graph on this slide presents temperature and thermal power in one selected building zone. The zone temperature is selected to be 24 degrees Celsius in the interval between 8 in the morning and 20. The user flexibility is increased to 1.5 degrees Celsius, while the comfort savings trade-off parameter is kept at 1 for all building zones. First thing that can be noticed is that in the price optimal operation, load is shifted to intervals with lowest electrical energy prices and best central HVAC system efficiency. So we can see that load is shifted to intervals between 2 and 6 hours in the morning. Also, it is interesting to see that in the case without the battery storage system, the building peak power load is reduced by utilizing the thermal capacity of building zones. So we can see that the cooling in building zones is practically shut down, and we can see that the zone temperature is increased during the period when peak power occurs on the level of the overall building performance. In both MPC-based strategies, the temperature in all building zones is kept in the permissible temperature range around the zone temperature reference. The overall comfort in all building zones, which is measured as average deviation from the temperature reference, is improved by 57% in average. And more important, by utilizing pre-cooling in the morning, the overheating is reduced by at least 56%, which is especially important for south-oriented building zones. The estimated daily energy savings in case of the price optimal building operation are between 18 and 26%, depending on the comfort savings trade-off parameter, without becoming worse than current control in achieving thermal comfort. It's interesting to see that the majority of savings is a result of the coordination rather than of the energy storage possibilities. So I would conclude the presentation with saying that the true utility of the MPC is not only in the confirmed energy savings, but in the flexibility and modularity of the approach, which is ready to include all the challenges the future is bringing to us, from improved users' comfort, volatile energy prices, and in the end, the provision of ancillary services one day. So if we want to bring our buildings into the smart city arena, MPC is definitely one of the best tools to do so. Here is the list of the regional scientific contribution of the thesis. I think that there is no need to go through all of them because I already presented you all of them. And this is list of the most important publications. So this is all for me. Thank you for listening, and I'm ready for the questions.